students. I hope you were able yesterday to understand and start to apply those steps for balancing equations. Yesterday, in fact, you were given a practice a chemical equation to balance. We'll get back to this at the end of the period today. But before we get to that, there's one more thing I'd like to talk about regarding our notes for this week, and that is not all chemical reactions are the same. We went over indicators a couple days ago, but there are different kinds or types or categories of chemical reactions. We're going to mention the first two of these types of reactions today, and next week, we'll focus on the next two. So let's begin in our notes where we left off yesterday, and that is not there, but rather here. The four types of chemical reactions. The first one is called synthesis. The word synthesis means to put together. In fact, a synthesis chemical reaction is when two or more simple substances combine to form a new, more complex substance. It is the example that I've been giving you for a while now. The practice equation that you were to work on is an example of a synthesis reaction. Hydrogen an element, oxygen an element, two simple substances combining to form a new, more complex substance, a compound we call water. The other example we went over yesterday with magnesium. Magnesium, a simple element, oxygen, a simple element. Those two simple substances combine together to form a new, more complex substance, a compound called magnesium oxide. So you're a little bit familiar with synthesis chemical reactions, but you're going to need to be able to recognize, identify, and distinguish between the four types of chemical reactions. So I want to give you some tips, clues, and advice here on how you can do that. Each of the four types of chemical reactions have what we call a general format. And each of these general formats use variables. Now, in math class, I know you've learned about variables like 2x equals 4. That x is an unknown, until you solve for it and you figure it out. Well, in chemistry, with the general formats of these four types of chemical reactions, we use variables as well. And I'm emphasizing that because these letters here in the general format are not symbols. The A, B, and C here are not symbols. They are variables. Let me explain what I mean. With this general format, the first thing I really want to point out to you is simply this. If you look at the reactant side of the equation, to the left of the yields arrow, if you look to the left of that, you see two things, whatever they might be. In this case, and I apologize for that flopping of the hand and the cursor here, but if you look at the two simple substances, they can be any simple substance, mostly usually elements, but A and B are the variables that can represent simple substances. But the key clue here is what I've circled, the plus sign. When you see an equation that looks like this, that there are two elements or simple substances combining together with a plus sign, and there's only one thing over on the other side, on the product side of the equation, in this case represented by the variable C, a more complex substance. This is the general formula for a synthesis reaction. Let me put this into practice so that you can see what I'm talking about. Here I'm giving you two different examples. In the first case, we've got Na. By the way, anybody know what Na is the symbol for? Sodium. We've got sodium, which is an element, and we've got a plus sign, and we've got another element symbolized by Cl. Anybody know what Cl is the symbol for? Chlorine. So we've got two simple substances, sodium and chlorine. And by the way, even if you didn't know what those symbols represented, you can still see that they are simple substances. Even if you don't know their names, we've got a symbol here, combined together with a plus sign. Again, that's why I circled the plus sign. Look for that clue, that key, that plus sign. And that yields, arrow symbol, a more complex substance. In other words, compound. And you can tell that even if you don't know what these symbols are, you can tell that there are two different symbols, capital N lowercase a, capital C lowercase l, all together written as a formula as one substance that is obviously more complex than either of the two substances on the left. So here's one example of a synthesis reaction, in addition to the two I already mentioned. Now, here's another one. In fact, this one we're going to be doing in the laboratory. In the laboratory, you're going to be taking some of this element here, Cu. Anybody know what Cu is? Copper. We're going to be taking copper powder, and we're going to be heating it up in the presence of O2, which is, hopefully by now you're familiar with oxygen, to yield a new substance, CuO, which we'll call copper oxide. So if you look at this equation, notice the key, the clue, the hint. I've given you the plus sign. There's a plus sign in the reactant side of the equation, not the product side of the equation, that adheres to the general format of a synthesis reaction. So a synthesis reaction is like an addition problem in math. I hope that helps you out. That brings us to the second type of chemical reactions, which is called a decomposition reaction. And a decomposition reaction is the opposite or the reverse of a synthesis reaction. It's like subtraction instead of addition in math. A decomposition chemical reaction is when a complex substance breaks down into two or more simpler substances. So again, if you read the description of both synthesis and decomposition, they're opposites of one another. So let me give you a general format of a decomposition reaction. Again, using variables here in chemistry, we're starting off with C. What is C? No, it's not carbon. It is a complex substance because it's a general format. And this complex substance is the reactant. And this reactant is yielding, arrow symbol, two or more simpler substances. Well, how do you know if there's two or more simpler substances in the product side of the equation? Again, you look for that plus sign, that addition sign on the product side of the reaction. It is the opposite of synthesis. So again, let me give you a specific example here to help you out. Here's a simple example you've seen this week already, and I'm sure you've seen it before. Maybe some of you have done it at home. But we're taking a more complex substance here known as, what is this? This is a complex substance. and it is sodium bicarbonate. And this sodium bicarbonate, under the correct conditions, can break down into two or more simpler substances. And in this case, it's water and carbon dioxide gas. And I'm a little bit tired today, I have to be honest, and this is not sodium bicarbonate. I apologize. This is carbonic acid. Carbonic acid. Let me correct myself. This is carbonic acid, otherwise known as soda water. If you've ever taken a bottle of soda and you've shaken it, and then you open it up in someone's face, you have such laughter and enjoyment, right? And if you have friends like that, boy, you don't need enemies. But what you are seeing is a decomposition reaction of carbonic acid. Or if you just pour soda of any kind into a glass and you watch it fizz and bubble, you are watching a decomposition reaction of carbonic acid. That carbonic acid is breaking down into water and carbon dioxide gas, which is being released as a gas. That's what this little green arrow indicates. It's a gas being released. This is what makes soda flat. Personally, I actually like flat soda. I know not everybody does, but I don't really care for the fizz because it makes me burp afterwards. I actually like flat soda because I just like the flavor of it without the fizz. So I tend to either pour my soda real high to get all the bubbles out, or I might let it sit for a while to let all the bubbles get out. But in either case, the carbonic acid here is decomposing chemically into water and carbon dioxide gas. And of course, you have all of these sugary flavoring ingredients added in as well, which is why flat soda simply tastes like flavored water. It's because it is. All the carbon dioxide, all the fizz, all the bubbles have been released due to the decomposition reaction. That's why soda bottles are packaged under pressure. The pressure of the bottle is what prevents or slows down the decomposition reaction of carbonic acid here. But again, an example of decomposition, and look for the clue. The clue is no plus signs in the reactant side, a plus sign in the product side. Decomposition reaction. So review the synthesis and the decomposition reaction. We'll be talking about the second two next week as we further explore those types of reaction. But now I want to get to your homework from yesterday. I gave you this equation to balance, and I just want you to check your work and see if you followed the same steps that I followed. Anybody remember what step one is? If you don't remember, just look up in your notes and say it out loud. What is step one, everybody? Identify elements. Identify the elements. So that is the first step of balancing equations. You identify the elements, and what you do is you look at each side of the equation. Look at the reactant side. We've got hydrogen. We've got oxygen. We list them. Over on the product side, we've got hydrogen. We've got oxygen. We list them. And I'm going to give you another hint along the way here. Always prepare your lists of elements on both sides of the equation in the same order. Because as we get to larger equations, when you are comparing back and forth, it's going to save you a lot of aggravation and mistakes if you are simply able to compare straight across as opposed to hunting down lists of different elements. But nonetheless, step one, identify the elements. Who remembers step two? If you do, call it out. Step two is count the atoms. Count the atoms. So again, use the subscripts to help you. How many hydrogens do we have in the reactant side? 2. So we write that down. How many oxygens in the reactant side? 2. So we write it down. How many hydrogens do we have in the products? 2. Write it down. And how many oxygens do we have in the products? 1. Write it down. Now, I forgot to emphasize asking yourself the question before, did you create or destroy any elements? And the answer is no. You've got hydrogen and oxygen on both sides. But now that you've counted the atoms, do you have the same number of atoms of hydrogen on both sides? Yeah, so far so good. Do you have the same number of oxygens on both sides? The answer is no. So what does this show? It shows that you are a lawbreaker. Well, not really. It shows that this is not a balanced equation, which means we have to continue. So when you're asking yourself, have you created or destroyed anything at this point in time? You can say 2 equals 2, so that's cool, but 2 does not equal 1. This is a false statement. This is not a balanced equation. So we got to move on to step 3. And what is step 3, everyone? That's right. Change coefficients. So I've drawn little boxes here in front of each pure substance because remember, that's the only place you can put coefficients in order to alter proportions to get this recipe right, to get this chemical equation balanced. So ask yourself the question when you're looking at this equation. We can see that 2 does not equal 1. We go to the side of the equation with the smaller number. 1 is smaller than 2. And ask yourself, what times 1 equals 2? Hopefully from yesterday, you remember that little bit of math. 2 times 1 equals 2. So where do you place that 2? You place it in the only place you can alter the coefficient in front of a pure substance on the side of the equation where the smaller number is. But remember the phrase from yesterday, whenever you make a change, again, whenever you make a change, you must recount. So let's recount everything here, folks, okay? Let's go to the reactant side of the equation. How many hydrogens? 2. How many oxygens? 2. Product side of the equation. How many hydrogens? Remember, it's coefficient times each subscript. So 2 times 2 is 4. And 2 times 1 is 2. So have we fixed the oxygen dilemma? The answer is sure we have. Yeah. But have we created another problem? And the answer is yes, we have. Because even though 2 equals 2, 2 does not equal 4. So that brings us to step 4, which is repeat until it is balanced. So we go through the steps again. We look at the side of the equation with the smaller number. 2 is smaller than 4. Ask yourself, what do we multiply by 2 to equal 4? And hopefully you know the answer is 2. But whenever you make a change, so let's recount here. So how many hydrogens do we now have in the reactant side? 2 times 2 equals 4. How many oxygens? 2. How many hydrogens? 4. How many oxygens? 2. Does 4 equal 4? Uh-huh. Does 2 equal 2? Uh-huh. Now you can give yourself a round of applause because if that is what you got for balancing the equation, the recipe for making water, then you have balanced the equation, and that equation is the right recipe, and it does not violate the law. So good job. Good job. If you're still struggling with that, guess what? You're going to have the remainder of the period to do some practicing. I have written here for you, and you also have these in your book. In fact, I've given you a whole page of practice equations to work on. Here we have an equation between zinc and sulfur. I'd like you to balance it going through all 4 steps. Here's another between phosphorus and oxygen. I'd like you to go through all 4 steps and balance this equation. Now, some of you may find these 2 equations pretty easy to complete, and if you do, then I'd like to give you some more practice, those equations in your book, and I want to give you some hints. For some of the challenging equations that I am providing you, I want you to remember to use your math laws to help you, like multiplying numbers on the inside and outside of parentheses. You may see some chemical equations using parentheses. And when you see parentheses, if there's a number on the outside and a number on the inside, just like in math, you multiply those numbers to get the total number. If you're struggling with this, focus on those first 2 practice equations that I gave you in your book and don't freak out, okay? Do the best you can. But for those of you that this is coming easily to, challenge yourself. Practice doing those other equations as well. And so for the remainder of your time today, work through these practice problems and feel free to watch these steps over and over again until you get them. So until next time, bye-bye.